With us, we have our two rock stars here. We have our CEO, Paul Sutton, and we have our CTO, Ismael Gomez, here for sharing everything that's going on with srsRAN.
Thanks, Laura.
You're welcome.
Hey, everyone. So we just have a quick update on the project. I'm going to talk to the ecosystem, some of the activities we've been doing, and then Ismael will dig into some of the technical details. So it's been a busy year. This is a view of our commit history over the past year, averaging about 200 commits per month. So one of the things we changed since last year was we changed the cadence with which we were pushing public releases. So rather than doing 2 a year, we're now doing 1 every 2 weeks. And so this is getting the implementations out to the community faster than ever. In terms of our community engagement, this is our discussion board. I'm sure many of you are very familiar with this. We're looking at about 4,000 visits per month to the discussion board, so a lot of activity going on there. It's great to see. In terms of our documentation, so we have documentation for both our 4G and 5G solutions. Over the past 12 months, we've had about 89,000 active users across both sets of documentation. So again, really, really good to see that engagement. And when we look at the geographical spread, and this is specifically for our 5G documentation, there aren't many places that we're not getting some interaction from. As you can see, the US is top of that list, so a huge number of US-based users of the software. In terms of academic research, so we maintain a list of peer-reviewed publications in which srsRAN is actually used, not just mentioned, but actually used. And I think we're up to about 330 articles in that list on srsRAN.com at the moment. One of our objectives for the srsRAN project is really to build a platform to enable that translation of research into products and services. And that's our guiding goal, and our work with AST Space Mobile is a really good example of where we've been successful in doing that. So if you're not familiar with AST Space Mobile, they're building a low Earth orbit satellite network for direct-to-mobile coverage for 4G and 5G. We've been working with them since, I believe, about 2017, where we implemented the first modifications to a 4G RAN stack to allow it to connect to an unmodified handset with a bent pipe architecture through low Earth orbit. So if you put a huge latency between your handset and your cell tower, how do you convince the handset that you're not that huge distance away? How do you spoof it, and how do you allow that connection to be created and maintained, and then to achieve high-speed broadband through that? And we did that very successfully with AST Space Mobile. They launched Blue Walker 3, which was their test satellite, a couple of years ago, and we've been testing and demonstrating with that platform. But last September, on September 12th, they launched the first 5 commercial satellites, and these are Bluebirds 1 through 5. And so they will soon enter commercial operation. And so that's a really, really good example of an innovation that started in the lab, built on top of srsRAN, where we were doing investor demos, showing them that this technology really can work, all the way through to commercial service with a groundbreaking new product and service. So as we went from 4G to 5G, we took a lot of the lessons learned from our 4G implementation as we built our 5G RAN stack freshly from the ground up. So we addressed all of the technical debt that had been built up in our 4G implementations and improved on everything when it came to 5G. And our objectives from the start were to provide a complete solution. So all of the components for the RAN stack within a single solution. So there's a lot of solutions on the market where you'll see layer 2, layer 3 solutions from one vendor, layer 1 solution from a second vendor, combining them together. We wanted to avoid that and to implement everything ourselves, including layer 1, both upper layer 1 and lower layer 1, and indeed the open fronthaul library that's key for interfacing with the open RUs. Portability has been critical to pretty much everything we've done. And so within the code base, we made sure that we were never tied to one specific hardware vendor. And so we've run demonstrations at Mobile World Congress earlier this year on the latest chipsets from Intel, AMD, and indeed from ARM. And we've gone beyond that, so we've implemented on FPGAs, on systems on chip. But it's a key design objective of the software is that you're not tied to a specific hardware platform. Performance is key, and I'll let Ismael speak to some of the performance achievements over the past year. In terms of flexibility, building in the interfaces from 3GPP, from O-RAN Alliance, from Small Cell Forum, ensure that this architecture is as modular as possible and where we can plug and play each of these pieces successfully. And I think we've done that. We've integrated with 7 RU vendors so far using Split 7.2 Open Fronthaul, in addition to our existing Split 8 RU solutions and SDR solutions. We've already integrated our Layer 2 and Layer 3 on top of a third-party Layer 1 system on chip for a small cell solution. And indeed, we've split our CU and DU and performed interoperability and integration with third-party CUs, in this case, with our DU. And finally, openness. And so that's why we're here today. So over the past year, one of the things we've started doing more and more is engaging in O-RAN Alliance Plugfest. And I just wanted to step through some of the work we've been doing there so that you may not be aware of it already. In fall of last year, we engaged with Orange Labs in France, and we focused on an end-to-end scenario where we implemented an srsRAN CNF on the Silva Telco Cloud platform in partnership with Lenovo. This is a snapshot from there where we have the RAN console running, the RAN running in Kubernetes, we have a Spectrum analyzer, and we have the COTS phone. And we successfully implemented and demonstrated that end-to-end solution, and it was the first RAN workload ever deployed using the Silva framework. In spring of this year, we participated in the Global Spring Plugfest, where we partnered with the University of Utah and ran automated end-to-end testing for inter-DU handover. So handover functionality was something that came at the start of this year, and so our partners in Powder helped us to carry out end-to-end testing of that inter-DU functionality. And we're going to push this further in the soon coming Fall Plugfest, again in partnership with the Powder testbed in the University of Utah, where we're going to take this outdoors and we're going to start carrying out end-to-end outdoor inter-DU handover. And this is facilitated by the Powder testbed's mobility solution, where they have COTS devices on vehicles, including buses that are traveling around the city, and they have an outdoor deployed testbed where we're exercising this handover functionality in a broader geographical area. Our second fall Plugfest activity is in partnership with i14Y Labs with Deutsche Telekom in Berlin. And here we're carrying out the complete reference test and integration focus group test suite on that end-to-end platform in i14Y. One of the things we'll be doing, interestingly, with that work is implementing all the mandatory functional tests and security tests, with the objective of achieving O-RAN badging and a certificate at the end of the Plugfest. So moving on from Plugfest, I wanted to talk a little bit about the approach that we take within SRS towards licensing, and the reasons we do that and the objectives and what we've achieved with it. So obviously source licensing is the heart of everything we do. Our business model is dual license. So we open source under the HEBL v3, which is the srsRAN project that you're very familiar with. And we also provide commercial licenses for the same software, essentially, which we call srsRAN Enterprise 5G. One of the benefits of this dual license model is that it ensures sustainability of the project. And so I just wanted to talk to that a little bit. With the open source, we've been able to bootstrap this entire effort. It's allowed us to build up an extensive community, and it's allowed us to collaborate with a huge number of partners across R&D projects, both in Europe and in the US. In Europe, we've worked with the European Space Agency under Horizon projects. In the US, we've worked with NIST under DARPA, of course. And this activity has all driven commercial engagement. So as we've been able to demonstrate the capabilities, we've been able to engage with commercial clients and partners. But the key benefit of having that commercial engagement, and Tracy touched on it, was that as soon as you have a paying customer, they're going to be very demanding in terms of the performance and the functionality that you're delivering to them. And so if you really want to test all of the corner cases of your solution, if you really want to test the long-term stability of your solution, deploy it in the field, and you'll very soon see where the issues lie. And so through that field deployment, we've identified the corner cases, the bugs, the performance issues within the code base. We've addressed them with those partners, and all of those changes go back into the open source code base, which benefits everybody. And so this cycle is really the key to the quality, to the cleanliness of the code, and the sustainability of the project as a whole. Next, I want to talk a little bit about interest in open source RAN, specifically here in the US, because there's a couple of things going on that everyone might not be aware of, but which are very interesting to watch the trends. So this is a memorandum from the Undersecretary of Defense for Research and Engineering, which came out at the start of 2022. And so this memorandum specifically highlighted open source, the importance of open source CU and DU solutions, the importance of open source RAN solutions, encouraging the at-scale industrialization of a 5G RAN specifically based on open source. This was followed up later in 2023 with an RFI, a request for information and a market survey on vendors who had a capability to provide an open source CU and DU solution. And as SRS, leading the srsRAN project, we submitted a comprehensive response to this, putting our hands up and saying, we're prepared to provide the open source CU and DU, which in this case, the US Department of Defense is looking for. And in it, we highlighted some of the key requirements that we felt were needed for such a solution. And we highlighted openness. So by openness, we specifically meant released under an OSI approved open source license. By completeness, we highlighted the need for an entire solution covering layer 1, 2, and 3. It's essential to have that entire self-sufficient solution that doesn't depend on major third-party components in order for it to be used. Obviously, we highlighted performance. We highlighted the necessity of a sustainable business model. So there's no point in releasing an open source solution for CU and DU this year if you can't then continue to develop it and ensure that it is sustainable in the long run. And that comes down to developers, a point that Tracy touched on as well, and SJ, where if you don't sustain the developers that are feeding into an open source ecosystem and into a project, then it's going to die, it's going to wither on the vine. And finally, community as being critical to ensure that sustainability going forward. So building on top of that activity in 2023, 2024 had two key events that I want to highlight. The first was in April. So this was the LF1 Summit Open GovCon 6G Innovation Day, where 5 key US government agencies came together specifically to discuss the future of competitive innovation built on open source and open standards. And obviously 5G RAN and Future G played a major role in that. And then just last week, we had the NITRD workshop here in Washington, which focused on a robust and sustainable open source software ecosystem for future wireless R&D. And so clearly there's a interest and a recognition of the importance of open source RAN in the broader context here in the US. And tomorrow morning we'll hear from Dr. Tom Rondeau, the Principal Director for Future G at OESD R&E, specifically talking to that topic and highlighting the vision for Okudu, an open source CU/DU solution. And finally, I wanted to share something I was playing with over the weekend. So this is essentially I was looking at ways to visualize the code base for our 5G RAN stack and what sort of insights we can get from that. And so before I hand over to Ismael, I just wanted to share some of this with you. So this is a map, and this is it looks at the file sizes within the srsRAN project code base. It's a very crude measure of complexity and comparing the complexity of different components within the code base, but I thought it was quite interesting. And so this is a breakdown. We've got the lib folder, the tests folder, the include folder. Okay. First thing that I noticed, a huge part of the code base is made up of tests, which I think is a very, very positive sign for the code base in general. Drilling down a little bit further, we see that huge sections of it are made up of the ASN1 message pack unpack code, which is automatically generated. So maybe not as interesting. So the next thing I did was, okay, strip out the ASN and see where we stand. Okay, this is a little more interesting. So now you can see that the tests make up 36% of the overall code base. So I thought that was pretty interesting. But then drilling down further, you can start to look at what components of the RAN stack are really occupying the majority of that code base. And so we can see here within the lib, which is really the implementation, it's the physical layer and the scheduler are the top two elements, so Phi and Mac, followed by CUCP and then on further. This is kind of reflected in the include files as well, where you can see that the physical layer really dominates, followed by the RAN, which is really a lot of the control procedures. And then within the tests as well. So again, you've got that physical layer, the scheduler, and I think this reflects what anybody who's worked in developing code knows, is that as you look at the RAN stack, I would argue that the complexity increases the further down the stack you go. And I think that's reflected in the code base. But I just wanted to share that. I thought it might be interesting. And with that, I'm happy to hand over to Ismael Gomez, SRS CTO and founder of the srsRAN project.
Do we want to take questions on the project updates?
No, we'll take it.
No?
Yeah, I think it's easier.
Okay, so thank you, Paul. I'm going to talk about a little bit about the technical updates. As Paul was saying, yeah, it's been a year. A lot have happened. Last year we were explaining how we started the project, where did we came from, the 4G repository, the new repository. Since then, 3 major releases, and as Paul was saying, nearly every month, or sometimes even more frequently, we do code pushes, code releases. We are still following the same 2 tags per year, so very soon you will see the 24.10. And I will talk later why or how can we achieve these monthly regular code updates. As you can imagine, is thanks to a very robust CI/CD that we use. I remember last year I was super proud of this achievement. I think that I still cry when I think about it. We were doing 1.4 gigabits per second, so we were coming from 4G. Our top rate was 150 megabits. Now we were doing 10 times that in a large server. We were using 7 cores. It was 4-layer downlink MIMO, and we were using the TM500 from Viavi to test it, which is like the industry standard product to test your DU. So it was like a massive achievement. The entire team was super proud. But if you look at what we can do this year, we are able to run 12 of these cells in a server. We have this server in the lab. It's a 16.4 core and AMD, and we can run 12 of these cells simultaneously, achieving a total of 18 gigabits per second in the downlink and 1 gigabit per second in the uplink. If you think about it, it's massive, the improvements that we have made to be able to sustain this. These are not 12 DUs running in virtual machines. This is a single executable running 12 cells, coordinating the threads. And one of the things that has improved a lot and made this possible also is the memory optimization. If you start scaling up, even if you have many cores, if you start scaling up the number of cells, you soon will realize that the memory is a bottleneck. Tomorrow, don't miss the presentation from Xavier. He's our Phi guru, and he will explain a lot of the details of what improvements we have made in the last year and what made this possible. I also put here this, the 4 cores per cell. This is more or less the number of cores that we need of this CPU to run. And 22 watts per cell is more or less the power consumption. And as Paul said before, portability is key for SRS and is key for the project. So we don't forget about ARM, and we have also improved a lot the last year, the performance in ARM. And we use the Ampere Ultra, which has 80 cores, and we are able to run the same number of cells. I think that we can push this a little bit further, but for now, this is more or less the maximum results that we get. You see that I also put here the power consumption. I didn't put them side by side because I don't want people to ask about power comparisons between AMD and ARM, because they are very different generations. This Ampere Ultra is quite old. And we also have gone to embedded. We are using now the NXP 2160, which is a 16 cores ARM, designed for low power, for more embedded DUs. And in this one, we can run 1 cell or 2 cells 2x2. And it's not only about performance, it's also a lot, we care a lot about stability and scalability in terms of number of users. So again, going back to last year, we were also very proud of being able to achieve at this test that we were running for 24 hours, 32 UEs, again using Viavi. But this test was only doing full rate downlink and uplink using UDP. So in the last test in the last year, we have increased a lot the number of tests that we do. I'll talk about this later. And for instance, using the same Viavi tool, we do what we call the stress test, where we have 16 UEs that are saturating the G0B, doing full rate traffic, and another 16 UEs who are simultaneously attaching and detaching every 5 seconds, stressing the control plane. And we make sure that this runs, again, for 24 hours with no lates, with no user disconnections. We do also tests with reestablishment and with handover. And this year also, as Paul was saying, talking about the Plugfest, we have had a lot of integrations with other organizations. And one example is Digital Catapult, which has been able to test, again, using the Viavi, more than 300 UEs. And when we want to go further than these 300 UEs and with multiple cells, we run many times into logistical problems. It's not easy to set up a lab environment with 12 RUs and many UEs on every RU. It becomes very, very expensive and very difficult to run. And what we have developed this year and have improved a lot is what we call the U emulation, or we call it test mode internally. And this is a way to emulate a large number of UEs and stimulate and exercise the MAC and the file layers. And this allows us to very quickly test if a platform, if a CPU is able to sustain a given load. With this, we are able to run in the same server where we run 12 cells, 800 UEs per cell. So that's a total of 10,000 UEs in the DU, which I believe that is an impressive achievement. Again, this we run for many hours, and we make sure that it's stable. This shows an impressive stability and performance of the full stack and scalability, and it wouldn't have been possible without a very good design and very good software architecture. So again, tomorrow, don't miss the presentation from Francisco, who is going to get deep into the DU, the software architecture, the threading, and he will explain how he made this possible. And so the CI/CD, as I said before, is critical in SRS also. Internally, we use this development workflow. Every time that a developer wants to create a new feature or create a bug fix, creates a new branch, develops it, when the code is ready, passes it to the repository, and we run what we call the merge request pipeline, CI. So that's a set of tests that run maybe 15, 20 minutes. If everything passes, it gets merged into the dev branch. And then every night, we run what we call the nightly, which is a slightly longer set of tests, probably 8, 10 hours sometimes, that runs overnight. With end-to-end tests, here we use the BAB TM500 in automation mode. When all these tests pass, the dev branch gets merged into next, and on Friday or the Saturday morning, we start what we call the weekly, which is 2 days of testing different platforms, different operating systems. And when all that gets passed, it gets merged automatically into the main branch. The main branch is what we release in the GitHub repository. So every Monday, if we have a green from the CI, we are confident enough that we can release that and it will be stable. And we test a lot. We do more than 4,000 unit tests and 140 end-to-end tests. The end-to-end test, we use GROMQ. Many of you are probably familiar with the Microsoft UE emulator. This test, we typically run it on the MR pipeline. And then we also have RF tests that, again, using a Microsoft UE emulator or CodeCUE. For the RF tests, we use USRPs, B210s, X, and we also use ORUs, and we also use a lot the BAB RE emulator. We combine all these with different distributions, different versions of the operating systems and GCC toolchain. And we use also other sanitizers and thread sanitizers to make sure that we catch bugs on memory and on threading. For the other sanitizer and thread sanitizer, the GROMQ is very useful because we can run the entire stack, the entire G0B stack in non-real time with a Microsoft UE. And we can attach 32 UEs, for instance, to handover and make sure that the threads and the memory is all good. In terms of the kind of test that we do, we start with very simple. With a single UE, we just attach. We do full rate, for instance. When we go to multiple UEs, we do, again, full rate, TCP, UDP. We do this attach and detach while doing traffic that I mentioned before. We do also handover tests. So these are 32 UEs from handovering from one cell to another in a kind of ping-pong fashion. We do this sequentially. We do this simultaneously. We do also reestablishment, so UEs reestablishing continuously in a cell. We do also paging tests. And with the BAB TM500, we have we emulate the channel using fading channel models or UEs moving at a speed. We have also improved a lot and expanded a lot the E2 interface. Last year, we were just starting with this. We just had minimum support for the KPM service model and only did integration with the FlexRig. This year, we have improved a lot and expanded a lot on that. I don't miss the presentation this afternoon, I think, from Justin, who will get very dive again on the details of the rig. We have developed also very cool applications like rig-driven handover. And usability is also super important for us, as you know. We have added a lot of tutorials, a lot of documentation. This is just a quick list. Brendan, I think that this afternoon is going to go through tutorial on how to set up the G0B and attach a UI. So also don't miss that. So it's been an incredible year in terms of performance improvements, portability, scalability, stability, but also we have added many new features. Probably the most important one have been the C on DU split. We have also integrated the DU with a third-party CU, a commercial CU vendor. We have added F1 handover. We have added reestablishment, which kind of improves on these RRC procedures. We have added RAN slicing. We can do static and dynamic PRB assignment. We have started with NTN support for Geo. I think that we probably expanded the number of RU vendors that we support since last year. This is the list of vendors that we have integrated with. And last year we had integrated with RU emulator from Viabit, and during this year we have also integrated with Keysight. And to finish my presentation, looking at what's next and what are we working on, this is the current list of work in progress features. So we are working on the separation of the control and user plane at the CU. We are working a lot on quality of service, on QoS-aware scheduling, on admission control. We are also working on DRX, measurement gaps for interfrequency handover. We are also adding sounding reference signals for 1 and 2 ports. We are starting to do O1 integration with an SMO, and E2, it's something that continues. We are continuing expanding the variables, the service models that we support. And all of these features, you can expect them to be available by the end of this year, maybe early next year. And what will be next during 2025, it's still a little bit up in the air. Depends a little bit on the directions of the R&D community. But these are the items that we have in the pipeline. FR2, higher numerology, we will start with 120 probably, carrier aggregation and dual connectivity. And then massive MIMO, supporting Cat-B ORUs, and low latency. It's still a little bit up in the air if we will start with this next year or maybe the following. And that concludes my presentation. If you guys have questions, I'll be happy to answer.